Good afternoon, all. We'll wait for few more minutes. We'll start at 3:05. Okay, it's 3:05. Let's start. So Priyansh was asking what is the link for these lectures. I'll share the link after the end of the session. Okay. Uh, okay, let's start. Welcome all. Welcome to fourth week of discussion session of the course Finite Element Method. The course instructor of this course is Professor Biswanath Banerjee and Professor Amit Shah, and I am your teaching assistant. Myself, Asif Raza. I am a PhD scholar from Department of Civil Engineering, IC Bangalore. So today we'll be discussing the solution of assignment number 4. But before that, I'll just ask basic questions to all, and I hope everybody will give the answer. So I'll just write the questions. It's better I'll write it in black. So question is, cosine is a class M function. So here M is what? Option A is 0, 1, option B 1, option C 2, option D infinity. So you guys can write your answers in using the chat box. What do you guys think? What is the answer? So I repeat the question. Cosine function is a class M function or if you guys don't understand, it's a written like cos function. Cos x, I suppose, is a Cm. It's called as Cm function. So what is m here? C0, C1, C2, or C infinity function? So what do you guys think? What is the answer to this question? I'll I'll give you a guess that the cosine function is called as a smooth function. Priyansh has given an answer as option D. What about others? Abraham, what's your guess? Okay, answer is option D. It's a C infinity function. Cosine function is a C infinity function. Cosine or sine, cosine, sine are C infinity function. So what are C infinity functions? Like if I say it's C1 function, so it implies that uh, if I take the derivative, say, if I call a function as Cm function, it implies that I can take the mth derivative which is continuous. It implies that uh, suppose uh, how should I say? So cos x, if I take the first derivative, if my fx is cos x, first derivative is what? Sin x, which is the continuous and differentiable everywhere throughout the domain. Then I take the second derivative, it gives what? Cos x, it's minus x, minus cos x. Third derivative, it is sin x, and it goes on. So this goes to infinity. So I can take the derivative of cos x infinite times, and the derivative itself are continuous all throughout the domain. So that is what C infinity functions. I hope this is okay. It's better I give an example of which is not, like if my fx is mod x, so what is my function? This will be the function, right? So if I take the first derivative f dash x, this is equal to 1 for x greater than equal to uh, um, 0 and minus 1, oh sorry, greater than 1 and s less than, sorry, 0 0, and it's not uh, f dash x is not defined in x equal to 0. So that says that fx has does not have first derivative at x equal to 0. That says that mod x is not a C1 function, and if I see the lower order C naught, so it is continuous throughout the domain. So mod x is a C1 function, sorry, C naught function. Okay. Yes. Similarly, there are few more examples where functions are C naught, C1 might not be C2. Okay. Let's move on to another basic question to our problems. Question is, what is the independent variable in the differential equation given below? And the differential equation is d square dx square b times d square w dx square plus k w equal to f. The options are x, b, second option is w, c option is okay. C option is B. I should write the option is B, C as W, and D as F. So, any guesses, please? I repeat the question: what is the independent variable in the differential equation given below? And the differential equation is second derivative of B times d square W by dx square plus kw equal to f. So what is my independent variable in this differential equation? Options are x, b, w, f. Guesses, please. I thought of putting such a simple question because you guys are solving complex problems, so you should know what is the basic stuff involved in these questions. So Priyans has given an answer as option A. Others? Come on, guys. No one else? Abraham has said option A. Okay, I'll move on. Yeah, so the correct answer is option A. You can see all the terms are differentiated with respect to x. So x is my independent variable. Okay. Mm, let's put one more basic question. Let me ask one more basic question. Okay, just basic question to previous assignments. So question is, for a fourth order differential equation in its weak form, so the differentiability of the residue is option A it's 1, option B it's 2, option C is 3, option D it's 4. So repeat the question. For a fourth order differential equation in its weak form, the differentiability of the residue is 1, 2, 3, 4. Answers. It's quite standard now because you guys are solving beam problems, so you must be knowing what would be the differentiability of my residue. Guesses, please. Anyone? Not even Priyansh this time. Weak form means you guys are taking me back. So strong form is what? It includes governing differential equation plus boundary conditions. Weak form is what? We multiply governing equation with weight function and integrate it throughout the domain. So this and this governing equation is multiplied with some residue, like this weight function is multiplied with the residue, and this residue is coming out with what? This residue comes with the use of governing differential equation. So when we integrate it and get the equation, we have a reduced order of the displacement or whatever we want to have. So suppose a governing differential equation, taking the case of beam problem, we have, what do we have? EI d4w dx4 plus q equal to 0, something like this, and the boundary conditions plus boundary conditions. So this is my strong form. What will be the weak form? We multiply it with weight function, suppose v times EI d, and better write like this, plus q equal to 0, and then we integrate it in this domain. Finally, what do we get is d square dx square EI d square w dx square plus EQ or something like this, plus some more terms equal to 0. So if you see, this is my weight function, this is what the residue, this was the residue, this was of fourth order. When we integrate it using integration by parts, the order of this residue reduces to second. So answer is 2. So I think you are lacking behind in this concept, so better go through the previous lectures properly. Okay, let's ask one more question and then we'll start discussing questions relevant to assignment. Okay. Okay, quite basic question. So in a beam problem, if displacements are specified at both the ends, or I should say if the displacements are known at both the ends, then options are option A, displacements at both ends will be referred as natural boundary condition. Option B, displacements at both ends must be homogeneous to solve the problem. Option C, displacements at both ends will be referred as essential boundary condition. And fourth option is none of the options are correct. I hope at least Abraham can give this answer. So the question is, in a beam problem, if displacements are known at both ends, then displacements at both ends will be referred as natural boundary conditions. Second option is must be homogeneous to solve the problem. Third is they should be referred as essential boundary conditions. And fourth option is none of the options are correct. So answers, any cases? Priyansh has given as answer C. Others, Walid also has said C. I expect Abraham to answer because this thing I have already told in previous lectures, previous sessions also. Okay, I think essentials. Yeah. So answer is option C. It's essential boundary condition. So okay, I'll just modify this same question. Okay, let me do this. So in a beam problem, if instead of displacements, if uh, bending moments at both ends are known, then so I'll just okay bending moments bending moments okay, so what will be the answer now? I just modified the previous question. I'm saying instead of displacement this time we are given with we know the bending moment at both the ends. So these bending moments at both ends will be referred as natural boundary condition, or they must be homogeneous to solve the problem. Third option is essential boundary condition. Fourth is none of the options are correct. So answers, guesses. Priyansh is saying C. Walid has also said option C. Mm, mm, yeah, Abraham has said bending moment is equal to force condition, normal boundary condition. Yes, I expected you to give answer. So with this, answer is option A, Norman boundary condition or natural boundary condition. So they are the same. Norman boundary condition or natural boundary condition. So answer is option A. Uh, to explain it, like if you guys have problem to understand like what is essential boundary condition and what is uh, natural boundary condition or Norman boundary conditions. So briefly I'll explain, like we multiply residue with the weight function, then uh, we use integration by parts. Okay, suppose, okay, I'll just use this EA by 2 d u by dx whole square dx. I'll explain through this. Okay, so let us take okay, EA du by dx whole square equal to q. Suppose uh, plus q equal to 0 with some boundary conditions. This is my governing equation. Okay, so for weak form, what do? We multiply with weight function to this residue EA du by dx whole square plus q dx. Suppose this equal to 0. Then we use integration by parts. So it will come out to be E A du by dx plus this will be my boundary and minus 0 to L dv by dx EA du by dx plus VQ dx equal to 0. So this will be my weak form. Okay, this is my strong form. So when in the weak form, in the boundary conditions, so this is my boundary conditions, right? So in the boundary conditions, the the weight function in terms of weight function, you convert the weight function in terms of my state variable which I want to study. In this case, v is my weight function. Convert it in terms of displacement, that is u. So this is will be my primary variable, or this is called my primary variable or essential boundary condition. Primary variable and the boundary specified with respect to primary variables, it gives me essential boundary condition or Dirichlet boundary condition. Dirichlet boundary conditions. Okay, this is what with respect to the primary variable and giving result essential boundary condition or Dirichlet boundary condition. For the natural boundary condition or normal boundary condition, consider the coefficient of weight functions convert weight function or its derivatives. Actually, to convert the coefficient of, directly I'll just write primary variable. If you understand the first, you can understand. So consider the coefficient of primary variable. So in our problem, it's E A du by dx. the coefficient of V is Ea du by dx. So this is called as secondary variable, and boundary conditions specified with respect to secondary variable, it's called as Neumann boundary conditions or natural boundary conditions. Okay. So in the case of beam problem, it's a fourth order derivative. It converts into a second order derivative, the weak form, and it will have a coefficient like this: d square v dx square ei d square w dx square, uh, and dv by dx. Uh, Sorry. Yeah, this was correct. And this is an dv by dx ei dq w dx q. I think this is the one. Let me see. Ei d4w dx4 plus q 0 if I multiply v d4w dx4 plus q ds integrated will have boundary terms v ei dq w dxq and dv by dx ei dx. Okay, I got it. So we'll have the term dv by dx times e and v. Okay, so this will be the boundary conditions pertaining to this. So the primary variable will be, if you see, weight functions are v and dv by dx. So the primary variable will be, convert this primary variable in terms of weight function, the state variable in consideration. So it will be w and dw by dx, that is displacement and slope, and our secondary variable will be the coefficients of this primary variable, and those are ei d2w by dx square and ei dq w by dx cube. So these are what moment and shear force. Okay. So these are Neumann boundary condition or natural boundary condition. These are essential boundary conditions. So as pertaining to the previous questions asked, if boundary conditions are specified, those are natural boundary conditions, and if displacements are satisfied, then specified, then those are essential boundary condition. And Abraham has typed Dirichlet boundary condition. Yeah, do you have any question pertaining to?
No, sir. That was in between. I typed it. When you told the essential boundary condition, I just typed it as
Oh,
then.
okay, okay, fine. So I hope this
Sir,
nobody.
a doubt.
Yeah,
In the
yeah.
second option, it's pertaining to homogeneous condition, right? So that will your
Yes.
second option. Uh,
Yeah, yeah.
so that will depend whether the method or it will depend on the method adopted, right?
Yeah, see, the questions, the option is displacements at both ends must be homogeneous to solve the problem. So the
Okay.
question this need not be correct, because I can specify my displacement. Suppose, uh, uh, mm, okay, take the case of bar problem. Okay, So one side is fixed. Either I can give a force so that I have to solve the problem, or either I can say the problem in the problem that this displaces by 5 suppose. So I am saying that so what is pertaining to this, the boundary conditions will be, one of the boundary condition will be like the displacement at x equal to 0, x equal to L is equal to 5 mm. So this is not homogeneous, but still I would be able to solve this problem, right? So this second option need not be, it's not the like hard and fast requirement.
Okay.
Okay. I think you are confusing it with the weight function uh, where I said that weight function should satisfy the homogeneous counterpart of the essential boundary condition.
Yes, yes.
So don't
Yes.
confuse that with this. This is displacements, actual displacement.
Okay, okay. Got it.
Okay. So like I said, so when I said UL equal to 5 mm, to solve this problem, we take what? V at L equal to 0. That will be my condition for my weight function. So that is not displacement, that is my weight function requirement. Okay. I hope this clarifies. And uh, I think I'll keep it some for the next discussion session. I like pre in the further sessions, like in upcoming sessions also, I'll try to keep such basic questions so that you guys have I can see whether you guys are going through the concepts properly or not. Okay, now let's discuss questions pertaining to the assignment number 4. So the first question was, identify the incorrect statement corresponding to a two-node beam element with a cubic Hermite interpolating polynomial. The element is shown below with the degrees of freedom as indicated, and the element spans between x equal to 0 to x equal to L. Phi I is the shape function corresponding to degrees of freedom I. The incorrect statement is, I think you guys already know the answer. I would like to know what's your view. How do you know? First of all, answers please. If any, have you been through the assignment solutions also or not? First that thing also matter. So answers,
Yeah. The incorrect one is option D.
yeah.
Since it is Hermite polynomial, the basic variable and its derivative will be continuous and its value will be 1 at x equal to 0. And option C is also right.
No, but okay. So option one is correct. Option two is correct. Option three is correct. So the incorrect statement of all these four statement is this option 4. So uh, if I say how to correct this statement, if I ask you how can I correct this statement, or say okay, leave it. Uh, Answer is this. Okay, if I ask you, we have like um, this is pertaining to what? Wx is equal to phi 1 q1 or v1 plus phi 2 theta 2 uh, theta 1 phi 3 v2 plus phi 4 theta 2. So all these statements are pertaining to this denotion. So one of the correct statement was phi 1 of x plus phi 3 of x equal to 1. And this statement, these functions, if you see, these are pertaining to what? The displacements. So if I ask you what will be the analogous of similar this equation pertaining to the slope, that is phi 2 and phi 4. So what do you guys think? What will be the equation? Hint is C option ABC all, and try to combine. I think you guys need to check it properly. So I'll just give you the answer. Answer would be, if you see, uh, equation C is phi 1x plus phi 3x equal to 1, and option A says like what, phi 1 at x equal to 0 it's 1, and we also know that phi 3 of x uh, at x equal to L is 1, right? Now if you see, we are given with the option B as d phi 2 by dx at x equal to 0 it's 1. Similarly we'll have d phi 4 by dx at x equal to L equal to 1. Okay, so if I combine these statements making analogous to this, my correct answer would be d phi 2 by dx plus of x mm, d phi 2 by dx of x plus d phi 4 of x, it's equal to 1. So this is what will have one more statement about this shape functions or interpolation functions. Okay, you can cross check with the functions we have derived. Okay, moving on to the next question. So consider the following prop cantilever beam of length L, which is loaded in UDL for a half of its span, and answer the linked question number 2 to 4. The beam is attached with two elements of equal length, and the beam have constant EI throughout. The nodes and corresponding degrees of freedom are shown in the figure of the beam. Solve the beam for unknown generalized displacement of the applied load. And the question is, unknown generalized displacement of the beam along degrees of freedom 3, 4, 6 are denoted as U3, U4, U6. Final equilibrium equations containing all the displacements and known force will be. Similarly, we'll have displacement vector and moment. So I'll just I think you guys already know the answers, but I'll just go through it briefly, and if you guys have any doubt pertaining to it, you guys can ask. Okay, so let's start. So we are given with the problem two element, first element is loaded with a UDL Q naught. Okay, we have degree of freedom 1, 2, 3, 4, 5, 6. So for a single element, having 1, 2, 3, 4 with uh, Young's modulus E, I, length LE, the element stiffness matrix is given as this 2EI by LEQ, and this pertains to the degree of freedom this. Okay, and correspondingly if we have a UDL to this system, it is divided like this, 2, 3, 4. Okay, better keep this in mind. Now let us do this for our elements. So our first element we are given with Young's modulus EI. Length of element 1 is okay, L by 2, and length of element two is also L by 2. So the stiffness matrix KL,
Sir,
yeah,
it may be a blunder question, but in that FEL, that matrix is applicable only when the member is carrying UDL, right?
yeah, I told
WL
just
square by 12.
yeah.
So, uh, the other may
Actually,
carry a point load also, right? So, is it
yeah.
good that we remember this?
Okay, so uh, I didn't
No,
write
no.
that, but there
Oh,
is a external load as well. Uh,
okay.
like these are pertaining to. So I thought like I would write it differently. This is just for UDL. I told
Okay, okay.
earlier.
You told it, but I generally asked.
Okay,
So,
okay. No problem, no problem. Okay. So, mm, so first element is 2EI LEQ. LEQ will be L by 2. 8 to the 16. This will be 16. EI LQ 6 minus 3L minus 6 minus 3L, 2L square, 3L, oh sorry, L by 2, L by 2, this will be 4 by 2, L square by 4, and 6, 3L by 2, 3L by 2, this will be 2L square by 4, and I write this as symmetry. Okay, so these are pertaining to 1, 2, 3, 4. Okay, and for the second element it will be similar, 6 minus 3L by 2 minus 6 minus 3L by 2, and that will be equal to L square by 2, 3L by 2, L square by 4, 6, 3L by 2, and L square by 2. So this is pertaining to 3, 4, 5, 6. Okay, 1, 2, 3, 4, 3, 4, 5, 6. So when we okay, so when we write the kg global stiffness matrix, it will come out to be, so if I write it like this, okay, so 16 EI by LQ, 1, 2, 3 kg equal to 16 EI upon LQ, 1, 2, 3, 4, 5, 6. So it will be equal to 6 here. Better copy this, minus 6 minus 3L by 2, L square by 2, 3L by 2, L square by 4, 6, 3L by 2, L square by 2. Okay, plus, and write it. It will be equal to plus 6 minus 3l by 2, right? And here it will be minus 6 minus 3l by 2 l square by 2, 3l by 2 l square by 4, 6, 3l by 2 l square by 2. Okay, symmetric. Here is 0 0 0 0. So simplifying it will get 4 ei upon lq. It will be 24 minus 6l minus 24 minus 6l, then 2l square, then 6l l square, then 48 0, then 4l square, it's 0 0 0 0 here, then here it's minus 24 minus 6l, this is 48 for l square, 6l l square, 24 6l 12 square. Okay, pertaining to 1 2 3 4 5 6. So this is our global stiffness matrix. Now for the load vector, so FEL for 1, this is pertaining to UDL only. Okay, so that was Q naught LE by 12 6 LE. So for 1 it's Q naught LE by 2, that will give me 24, and here it will be 6 and minus LE. LE is L by 2, then 6 L by 2. I think I'm right. Yeah. So this can be simplified as Q naught L by 12. Does it need simplification? Let me see. 24. Okay, I can write this as Q naught L by 48, and this as 12 minus L 12 L. Okay, so this is pertaining to my degree of freedom 1 2 3 4. Similarly, for the element 2, we can write Q naught L by 24 6 minus L by 2 6 L by 2, but in that case Q naught is 0, so this will be what? 0 0 0 0 for the degree nodes 3 4 5 6. These are all pertaining to my UDL. Now if I had written like for the element 1, like at the node itself, if there are any loads provided, so let us I'll just write Q1 Q2 Q3 at 1 and Q4 at 1. Similarly, Q element of 2 is, I'll write it as Q 1 odd, or I have 3 there, and the second element 3, this is 4, Q5 4 at due to 2, 5 due to 2, 6 due to 2. Okay, now assembly will be what? Kg times times degree of freedom U times force. So F is F global plus Q global. Okay, where F is due to my distributed load and Q is due to the point loads at the points itself, at the nodes itself. So this will be so if I write Fg, so that is so Q naught L by 4 minus Q naught L square by 48, then Q naught L by 4 and Q naught L square by 48. This is pertaining to that, and 0 0 pertaining to 1 2 3 4 5 6 degree of freedom, and my Qg, I will just write it as in a simplified form as Q1, Q2, Q3, Q4, Q5 and Q6. Okay, and seeing the question, it's a question is the point loads at 4, 5 and 6. It's not specified. Oh, sorry. There is a okay. And we have 1 2 3 4 5 6, and we have our displacement vector as u1, u2, u3, u4, u5, u6. Now the question we have is this. Okay, Q naught, we have 1 2 3 4 5 6, 1 2 3 4 5 6. According to the question, what will have u1, u2 and u5 equal to 0, right? So unknowns will be u3, u4, u6. And if you see the question, uh, the unknown forces will be pertaining to the known degree of freedom. Known degree of freedom will give pertains to unknown forces. So that will give me an unknown degree of freedom will make known forces to be 0. So we have u3, u4 and u6 to be unknown. That will imply like q3 and q4 and q6 equal to 0, as there are no point load applied at 3, 4 and 6. 3, 4 and 6, and q1, q2 and q5 are my unknowns. Now let us do the assembly. Okay, so we have to write kg times q equal to f, right? So that's a very big question. Okay, I'll just simply, so the way How do we solve it? So we have u1, u2, u3, u4, u5, u6. This we have, this I can write q0 by 4, q0 L square by 48, q0 L by 4, q0 L square by 48, 0, 0, plus this will be q1, q2, 0, 0, q5 and 0. This is so this is 0, this is 0, and u5 is 0. To solve this, we'll have in the global stiffness matrix, if we can just use, first of all, what we can do is assemble everything in terms of u1 or u4, u3, u4, u6, later on u1, u2, u3, u1, u2, u5. So if I write these things, okay, if I write my u3, u4, u6 as unknown, right? So I'll just okay, un, I'll write it as un, u3, u4, u4, u6. I'll write known uk as u1, u2, u5. Then likewise my known forces as unknown forces as and these are known forces. I'll just write it as okay. So 1, 2 and 5 will give me unknown forces, right? 1, 2, 5. So I'll just write R1, R2, R5, and these are known forces are R3, R4 and R6. And here you can observe R1 is equal to Q0 L by 4 plus Q1, right? R2 is minus Q0 L square by 48 plus Q2. R3 as Q0 L by 4 plus Q3. R4 as Q0 L square by 48 plus Q4. R5 as 0 plus Q5. 6 as 0 plus Q6. Okay, and these are 0, this is also 0, and okay, I made a mistake here, this is not 0. Okay, and what will be 0? Q4 is 0 and Q3 is 0. Okay, so what we'll have now is we now have stiffness matrix. If I write all in terms of blocks, okay, so this if I write is as known, this is write as Kn, this as Nk, and this is Nn. Okay, so finally we'll have what I'm saying is this is Kk, this is Kn, this is Nk, this is Nn, this is Un, U4, U6, and this is UK, this is RK, this is RN. Right, so simply this will be equal to Kk times Un plus Kkn times UK times RK Knk times Un plus Knn times UK Rn. So for the first unknown, if we want to solve this, we want to solve Un Rn, right? This is our objective. For this, what we'll do, we know this thing, we don't know this. Okay, so U known is 0 0 everywhere, right? So this thing equals to 0. So with this, my Un is Knk inverse Rn. I substitute it in the first equation. I'll have Kk Knk inverse Rn plus Kkn UK equal to Rk. Right, and again we know this UK is 0 0, so this term will also be 0. So this can be simplified as Kk Knk inverse Rn equal to Rk. So this thing will give me Rn, and this equation will give me I've made a mess, so I better clarify. I'll just write how it's solved. Okay, so first write the global stiffness matrix. So it was 48 EI by L cube 24 minus XL minus 24 minus XL 0 0 to L square 6L L square 0 0 48 0 minus 24 minus XL 4L square 6L L square and 24 6L to L square. This are pertaining to U1, U2, U3, U4, U5, U6. Okay, I said I'll just move all the unknowns towards the top. So with that, unknowns towards the top, right? So that will be equal to 48 EI by L cube. If I write in terms of U3, U4, or better, I'll just going into such mess, which is this is equal to what, Q naught L by 48 times 12 minus L 12 L 0 0 plus Q1 Q2 0 0 Q50. Okay, so I'll just use the equation, like if this is first, second, third, fourth, fifth and sixth, right? So use only the unknowns, which are U3, U5, sorry, U3, U4 and U6. Use third, fourth and sixth equation. We'll have 48 EI by L cube. This is equal to, okay, so third, I better write this complete, minus 6L minus 24 minus 6L 0 0 minus 24, this is 6L L square 0 0, this is 0, and this is 6L minus 24, this is 6L L square minus 6L. Okay, so using third equation, we'll have 48 EI by L cube times minus 24 U1 U2 U, these are 0 0 and U5 is 0, so that will be okay, I'll just write it as 48 EI by L cube minus 24 minus 6L and 0, so 6L 48 0 minus 24 minus 6L L square 0 for L square 6L L square 0 minus 6L L square 6L to L square. This is with respect to U1, U2, U3, U4, U5, U6, and right hand side will have only 3 equations, and that will be equal to Q naught L, knowns are 12 L and 0. Okay, so this is this will be what will have Q naught L by 4 and Q naught L square by 48 and 0. This is what will have in the right hand side. So solving this will have this is 0, this is 0 and this is 0, so we're left with this, 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 this. There it is, 48 EI the L cube times 48 0 minus 6L 0 for L square minus 6L L square to L square U3 U4 U6 equal to Q naught L by 4 Q naught L square by 48 and 0. I hope I'm going in the same right path. I think this is 48 zeros minus xl for L square. This is what we are getting, right? 48 0 minus, yeah. So this is we'll have now solving this equation, we'll get u3 equal to u4 equal to u6 equal to, so u3 u4 u6 is equal to q naught by ei times 13 L4 by 6144 minus LQ3072, and this is 5LQ768. So this is pertaining to the second question to this problem. And further, when we want to when we substitute these values in the equation, substitute above values in equations 1, 2 and 5, will get the unknown q1, q2 and q5. With that, q1 will have as, if you solve it, we'll get q1, q2, q5 as q naught L by 128 minus 57 minus 9L minus 7. So this tells that q1 is equal to minus 57 q naught L by 128. q2 is q naught L square 9 q naught L square 128, and q5 is minus 7 q naught L by 128. So what is q1? q1 is, if you see my what was the given question. Question was, there was a 1 2 3 4 1 2 3 4 5 6. So 1 is shear force, mine is coming minus, so that implies 57 q naught L by 128, it's acting upwards, okay, at node 1. q2, it's 9 q naught L square by 128 anti-clockwise, and these are all at x equal to 0 or at if it is written A, B, C, yeah, at node A, at node C we have this is also minus, so that implies 7 q naught L by 128, and this acts as upwards, while we have q4, q3 and q6 equal to 0. Okay, so with that we'll have our answer as option B for this. option A for this, line anti-clockwise, and this acts as upward, and option C for this. So the question asked only MA and VC. So we also have VA is equal to, that is also equal to 7 by 128 Q naught L acting upwards. Okay. So before moving on to the this question, I'll just jump into the question number 8 and ask you all. Yeah, Rafael, you wants to say something?
Yes, I wanted to ask about the previous question.
Yeah, okay.
I wanted to ask, the lecturer used the opposite sign rule in this task, in the variation. I want to ask what will keep the same and what will change if we change the sign rule here. Because you consider here downwards positive,
Okay,
counterclockwise positive,
okay.
as I understood.
Yeah. So you're saying in the lecture, was this the sign convention used?
Yes, but as far as understood, in this sign convention, the stiffness matrix will be the same. We need to be careful only with the forces.
Yeah.
Yes?
So what I will say is, so whatever we are taking, like we are fixing our degree of freedom to be the same throughout, right? So for the forces also, the coming values, like it was coming minus here, like our degree u3, u4, u5, u6 values came out to be 13 L4 6144, and this came out to minus L cube 3072, right? So this implies uh, pertaining to this sign convention itself, which we are considering in our problem. I hope that makes sense.
Okay, but what I don't understand, we change the sign convention here, but we use the same matrix, it's the stiffness matrix, and also it looks like we use all the same. I don't understand what
Okay,
was
so
changed.
what changes? Uh, yeah. So if you see, first thing is we are taking a sign convention to be downwards. Then Q naught also acting to be downwards. So if you see, if you consider my general convention, uh, if you want to know why the it would be same, it's better go to the earlier governing differential equation, which is this, right? So uh, solving this will have d square v by dx square ei times d square w by dx square uh, 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 plus q dx qv dx plus some boundary conditions, right? So you're asking why there is a change now. So this is if I say in my governing differential equation itself, if my w and q, what I am following my sign convention, it is I'm just taking opposite of it, then the final the stiffness matrix pertaining to that will also be same. Only my degree of freedom sign convention, I'm just taking opposite of it. Rafael?
Okay, it means that we only need to be careful with elemental forces.
Yes.
Thank you. Thank you.
Okay. Rather solving this long equations. I'll just move on to the question number 8. And without solving this, how can we do this in a quick manner? So the question was, natural vibration of a beam under applied axial load P naught is governed by the following differential equation. Identify the proper weak form of the differential equation, which has strong form as this, and boundary conditions are denoted as qi, slope is theta. Integration is carried on domain 0 to L. The weak form is. So without uh, getting much into, like, without solving, actually we can uh, do it quickly, as in, like, take term by term. So this is similar to uh, the beam problem. So when I will solve it, do the integration by parts, I'll do 2 times integration. So the differential equation will come out to be what? When I integrate it with respect to the 0 to L, I'll have what? 2 times minus minus, it will get plus. So it gets like this: ei d2w by dx square 0 to L dx, right? And we'll have 2 boundary terms, okay, pertaining to the second one, p naught d square w dx square 0 to L. If I multiply v and integrate it, we'll have what? This is similar to my bar problem. So this required 2 times integration by parts. But this one will require only 1 time integration by parts, and this will give me what? dv by dx p naught dw by dx and dx 0 to L. And when I integrate it once, so this will have a minus sign and again some boundary terms. And on the RHS side, these are all on the left hand side. On the right hand side, we have 0 to L multiply weight function v and rho a omega square w dx. So this will come out to be the same. This won't change much. So this will remain as it is. Okay. Now assembling it, what will have? Assembling, we get 0 to L ei 2 times of weight functions derivative ei d square w by w dx square minus this required one dv by dx p naught dw by dx. And when I take this term to left hand side, it will give me minus v rho a omega square omega. These are integrated to dx 0 to L, and the boundary terms equal to 0. Okay. So if I see it, if I compare it properly, so the correct answer would be So we have a square di dx square. This is okay. This is also okay. This is also okay. So with that, solution will be this option A, I suppose. Let me check it. Yeah.
This is A.
Yeah. Okay, it's A. Option A is the correct answer. A0 Q1 theta 0 here. I had a question in this I wanted to ask you all, but I forgot. Let me recollect. I wanted to ask you one question. Q1, Q2, Q3, Q4. Okay, I forgot. Actually, I wanted to ask one question pertaining to this, but I forgot. So, okay, nevertheless, let's solve the question number 10 or question number 9.
Please ask as far as you remember.
Yeah. Yes, sure. Okay, the question number 9 was 4 cantilever beam ABCD are loaded with point load, UDL, triangular load, and parabolic load respectively as shown below. All of the beams are discretized with 3 node single element. Displacement of which Euler-Bernoulli beam cannot be captured exactly considering this element. So, answer is
Option D is correct.
so. Would you like to give explanation to this, if you know what?
Okay, I can try. The element is considered here is a free node single element.
Yeah.
It means in Euler-Bernoulli beam, the degree of this polynomial, let me see in my notes. It is degree of this polynomial is it is a Hermite polynomial, and usual Hermite polynomial degree is free, right? It's
No.
free.
Yeah.
Usual degree of freedom of the Hermite polynomial for Bernoulli bar, two nodes with two nodes is free.
Yeah.
So polynomial that we need a Hermite polynomial with 3 nodes require 5 degree of freedom. Degree of this polynomial is 5.
5. Yeah.
I believe it's clear for everyone. If
Yes.
one need to elaborate, I believe.
Yeah. I'll try.
He or she
You go on.
he or she should ask. Okay, so the question that is here is: can we solve this element? Can the approximation will be approximation is the exact? So in exact problem, if we consider governing equation for the beam, it will be the fourth derivative of u is equal to q, right? So if we consider parabola, it is a polynomial of degree 2. Integrating with 6 times or 4 times of the polynomial with degree 2 gives us the same degree of freedom as we consider in the Hermite element. So with this element, let's consider if we consider polynomial, it will be, for instance, for this polynomial x squared plus bx plus c, right? For instance, for this polynomial. If we integrate with 4 times, the degree of this polynomial will be.
You're going off track. I'll just
Okay, degree of the polynomial of exact solution will be 6, but Hermite polynomial has degree only 5. So we are not solving exactly with this element.
yes.
Therefore, answer is D.
Yeah. So
I believe if I was unclear, you should elaborate this.
yeah, for sure, for sure. So in normal lectures, you guys have studied that we take normally two noded beam element with uh, 4 degree of freedom, elaborated as 1, 2, 3, 4, like this. So for this, we just take Wx as C1 plus C2x plus C3 x square plus C4 x cube as our displacement function, approximated displacement function. So yeah, if you see, when we take 4 degree of freedom, specifically when we take two noded element, it had 4 degree of freedom. So that gave me degree 3 polynomial, right? So when I take, question says we take a 3 noded beam element, so our degree of freedom pertaining to this will be what? 1, 2, 3, 4, 5, 6, right? So for this, my Wx would be what? C1 plus C2x plus C3 x square plus C4 x to the power uh, x cube plus C5 x4 plus C6 x to the power 5. You see, when we take 3 noded element, we have 6 degree of freedom and it has a degree 5 polynomial. Okay. So what does this imply? When we take a 2 noded element, it has a degree 3 polynomial. So if my exact solution of is less than equal to 3, then this approximated solution will give me the same solution or the exact solution, right? Likewise, our exact solution of when we take a 3 noded element, it is equal to less than equal to 5, right? So the degree of our exact solution, is 5 or less, then our element, this 3 noded element, will give me an exact solution. So if you search through this, the exact solution pertaining to the cantilever beam when it's applied uh, point load, it's the degree of the exact solution is, first one is cubic, so that is 3, it's 4, and it's 5, and it's 6. So exact solution have a degree as this 3, 4, 5, 6, and our element consideration has what? A degree 5 polynomial in consideration. So the exact solution will match, we'll get the exact solution using this element when our point of consider or the solution is having a degree less than equal to 5. So with that, my answer A, B, C will come out to be exact, but we won't get the exact solution with this. I hope this makes it clear to everyone. So with this in, yeah, Rafael wants to, okay. Please wait. Okay. Okay. Uh, mm, one question similar to this, as we are saying again and again, uh, Euler-Bernoulli beam, right? Or better, yeah. Okay. So you guys must have studied. Uh, okay, I'll just write the question here. So, which of the following statements is not true about Timoshenko beam? Timoshenko beam. I hope you guys have been taught Timoshenko beam. I went through the lecture, but let's see how much you guys know. So the primary variables are displacement and slope. Second option, the secondary variables are force, shear force, and bending moment. Third statement is cross sections which are normal and plane to the longitudinal axis remain normal and plane to it after bending of the beam. And fourth option is none of this. So I'll just iterate what is the question. Question is, which of the following statement is not true about Timoshenko beam? First option is primary variables are displacement and slope. Second option is secondary variables are shear force and bending moment. Third option says cross sections which are normal and plane to the longitudinal axis remain normal and plane to it after bending of beam. And last option is none of this. So what do you think? What is the correct answer? Abraham says option C. What about Rafael?
I don't understand the second option, actually. What are the variables? Force and bending moments are boundary condition. We not consider them as variables.
Okay, I think you joined later to this class, so you don't know.
Sorry,
I'll
I'm late today.
yeah. So I iterated earlier, previous to this class. I'll just show this. Yeah. So I'll just briefly I'll explain. You know this that we have we get a weak form where we have some part of our equation and some part as a boundary condition, right?
Right.
So in the boundary condition, if you see there's some part which is in the form of weight function and some part in the term of our variable in state variable in consideration. So I took an example of the bar problem, and in that when I use the integration by part, I got this boundary condition. So we have this boundary condition. In this boundary condition, if you see the form of weight function, it's in V. So when we convert it in terms of the state variable in consideration, that is in U, we'll get our as our primary variable as U. Like whatever form we have as in the boundary condition of weight function or its derivative, we take those function as our primary variable. So for a bar problem, U is our primary variable. But if you see in the consideration of our beam problem, in beam problem you get the boundary condition like this: dv by dx ei times d square w by dx square, and one of other boundary condition is v times ei d cube w by dx square. So if you see the form of weight function, it's dv by dx and v. So our primary variable will be, when we convert this v and dv by dx in terms of our state variable, that is w and dw by dx. So these are my primary variables, and when we specify the boundary conditions to the primary variables, we get the boundary condition as our essential boundary conditions or Dirichlet boundary conditions. Now when we consider the coefficients of these primary variables in the boundary terms, like in this case it was Ea du by dx. Ea du by dx, though this is my secondary variables, and the boundary condition specifying with respect to secondary variable is called as normal boundary condition or natural boundary condition. So in the beam problem we have shear force and bending moment as our secondary variable. So I hope that gives a gist to what I was trying to ask.
Okay, thanks.
So with that, first and second statements are correct. Third statement says cross sections which are normal and plane to the longitudinal axis remain normal and plane to it after bending of beam. So Timoshenko beam digresses at this statement itself, like uh, the Timoshenko beam and Euler-Bernoulli beam have a difference at this point. This statement is satisfied by Euler-Bernoulli, but for Timoshenko beam this is not the case. So our incorrect statement is the option number C.
By the way, what does it mean? None of this. None of this means that all true or not true.
All statements are correct. Question was asked which of the following statement is not true. So we got, say, a third statement is an incorrect statement. So if all the three statements have been correct, then option would have been none of this. I hope that makes sense. That makes sense. Okay. Uh, it's a simple question. Suppose we are interested to find fifth natural frequency of a cantilever beam. The beam is analyzed using Euler-Bernoulli assumption. So as earlier I told, where we digress, Euler-Bernoulli has an assumption C also. So that's fine. So suppose we are interested to find fifth natural frequency of a cantilever beam. The beam is analyzed using Euler-Bernoulli assumption and two node element with Hermite cubic interpolation is used. How many minimum elements are required to capture this fifth natural frequency? So answers?
It was tricky one. The one where I
It was
got
tricky one.
the wrong answer.
Oh, okay.
As I remember, it was C.
Yeah. Answer is 3. I'll just explain it.
Interesting question. Interesting question.
Yeah,
We need
I do
to
have
take
one more question pertaining to this. I'll ask first. I'll try to explain how this came. Then I'll ask you, and I think I'll.
Actually, I can answer this question.
Yeah, okay. If you want to share your screen as well, you can go for it.
Okay. I need to share screen. I'm not prepared to share screen. I need to attach my monitor. Oh, I attach my planchette. So it's
You,
just the question is about the matrix, stiffness matrix dimensions. But we need to consider stiffness matrix dimensions after eliminating from them boundary conditions.
yeah.
So if we have cantilever beam and the dimension of global stiffness matrix is 4, one node element, 4. But we eliminate from them how many elements we have here?
With that's only we
2.
need to find, right? How many minimum elements we need to have to capture my fifth natural frequency.
So I forgot that we need to eliminate boundary conditions there, natural essential boundary conditions from this matrix. So I put D answer because uh, I I consider these problems as if we are finding eigenvalues from the global matrix, but we need to understand that we need to find eigenvalues from
No, but
shortened
I
matrix.
would have understood like if you had given an answer as option B, but how could you give the answer D? Like when you're saying that you forgot to remove the boundary condition. So if I consider one element has what 4 degree of freedom.
Look! It's a very silly question, very silly error because my global matrix has 4 by 4 dimensions. It
No,
has
no.
four eigenvalues.
Yes.
I consider this like this.
Okay.
Okay, I need to attach my planchette so you can answer. Sorry, I'm not prepared to writing.
You need time, or should I explain this?
Yes, I believe you give a better explanation.
Yeah. Okay. So two noded element, one, two, three, four. So two noded element. When we consider one element, it has 4 degree of freedom, right? Uh, Better not consider this. I'll consider a series of elements. Okay. So one element, two element, three element, like this. So this is n minus one element. This is nth element. Okay. So every element has sorry, we have n element. So how many nodes will be there? One, two, three, four. Likewise, it will go here. It will be n. It will be n plus one. So when we have n elements, we have n plus 1 nodes. Okay, at each node there are 2 degree of freedom associated to it. One is the shear deformation and one is uh, rotation, right? Okay, so we have 2 degree of freedom per node. So total degree of freedom equals to what? 2 times n plus 1, that is to n plus 2 degree of freedom. So you're saying global stiffness matrix. So our global stiffness matrix will have a dimension 2n plus 2 by 2n plus 2. Okay. But we have to for finding natural frequency, we don't directly solve in terms of global stiffness matrix. We solve in the reduced stiffness matrix which is solved when we remove pertaining to the constraints. Where so constraints are like, if we fix here, so we have to remove this two displacements, two degree of freedom. So a reduced stiffness matrix will have a dimension of 2n plus 2 minus 2 by 2n plus 2 minus 2, that is 2n by 2n. This is what will have the dimension of reduced stiffness matrix. So a reduced stiffness matrix has a dimension 2n by 2n, okay, and will have 2n eigenvalues, right? So 2n eigenvalues, that implies 2n, if I solving frequency problem, so 2n frequencies, eigenfrequencies, uh, better leave this here. So 2 times 2n eigenvalues, we want to have fifth natural frequency, that is 2n should come out to be greater than equal to 5, right? So that we can capture fifth natural frequency. So this is equal to 5 by 2, that is n is greater than equal to 2.5. So n should be minimum. If you are taking minimum, it should be equal to 3. So this is what the answer would be. Answer would be option 3. Because if we take two elements, 1 2 3, this is what 1 2 3 4 5 6, 6 minus 2, that will give me 4. So we won't be able to capture our fifth natural frequency, so we need to have at least 3 elements, okay. uh, just a simple modification to this problem. uh, I'll ask, question is, what will be the answer to the previous question, previous problem, if our element in consideration is 3 noded element. Answer is 1 2 3 4. So I hope you got the question. What I want to ask, I'm asking, this was the earlier question. We wanted to find the fifth natural frequency of a cantilever beam using Euler-Bernoulli assumption, and the two noded element with Hermite cube interpolation was used. So how many minimum elements had was required to capture this fifth natural frequency instead of two node?
Can I
Yeah, sure.
try to ask?
Yeah, sure.
Okay, if we consider three nodal element, then we have 2 multiplied by n plus 2 plus 1 global stiffness matrix dimension. So 2 n plus 2 plus 1 minus 2, it will be for cantilever beam. Let's consider how much is this. 2n plus 4 plus 1 minus 2. It is equal to n plus 3, actually. So 2n plus 3 is for cantilever beam should be more than how much frequency do you have?
Fifth.
Do you
We
want
want to
fifth?
have the fifth natural frequency.
Okay, it will be 2n plus 3 is greater or equal than 5. It will be 2n plus 2 n is equal to more than 1. So n equal to 1 is okay for 5 uh, frequencies.
Are you sure?
No, you heard you heard my thoughts about this. My mistake can be my mistake could be that my generalized formula for um, elements doesn't work, but I believe it works because I check it for 2 elements.
Okay, I'll just. I think you are wrong, but let's say how if I'm able to explain or not. Okay, so we have a three noded element. If you see
Yes.
three noded element.
Three node element. Yes.
Okay, so uh, let's take case by case. What if I have only one element? Okay.
Okay, I'm not okay with my answer because for one element it gives me reduced matrix dimension 4.
One,
I'm
one,
not
two, three,
happy
four.
with that. I need
So,
to check my formula.
yeah, yeah. So I think you are, yeah, you have gone. You have understood that you have made a mistake. I don't know where you have made a mistake. So, okay, let's see. When we are taking a case of one element only, so we have a six degree of freedom element, right? So for this we have a 6 by 6 global stiffness matrix, and when I reduce it, when I remove the essential boundary condition, will have a dimension of 4 by 4. So this will capture only 4 natural frequencies. uh, okay, I should better global degree of freedom,
Okay.
global stiffness, reduced stiffness. So this won't capture case
I
1.
got the answer.
Case 2. I see. So case 2,
The
when we have a,
global.
when
Let
we
me.
ha-
Let me. Let me give the
let
correct
me at
option.
least complete it, then
Yeah, yes, because I gave a wrong answer. I should I should correct that because I'm shy about my incorrect answer. The global matrix dimension will be 2 multiplied by n plus 2.
come again.
The global dimensions of a global stiffness matrix is 2 multiplied by brackets n plus 2.
N plus 2,
Yes,
where n is
n is a number of elements in the consideration.
okay, number of elements. Uh, Let me check. So if I have one, two, three, okay. Say this has 1, 2, 3, 4, 5, 6, 7. When we have two, we have five. So uh, when we have one element, we have two nodes. Sorry, three nodes. Three nodes. When we have two elements, we have five nodes. So when we have n elements, we'll have what? 2n plus 1 nodes, right? So
It's for two nodal element
yeah,
or what?
no, three noded element. I specifically said right, three noded
Ah,
element.
okay.
So when we have one element, it has 3 nodes in total. So when we have elements, right? So each element has 3 nodes. So this is having like first element, this is second element, so it must also have one more. So total nodes 5, right? So if
Yes.
I have n number of elements, 2n plus 1 nodes will be there. So global stiffness matrix will have 2n plus sorry, yeah. So global stiffness matrix will have 2 times of 2n plus 1, 2 times of 2n plus 1, that is 4n plus 2, 4n plus 2. Okay, and when we reduce it, stiffness matrix, what will have 4n by 4n, right? And this will give me 4n eigenvalues, and 4n must be greater than equal to 5 to capture my fifth omega n. So n must be greater than equal to 5 by 4, that is n must be greater than equal to 1.25. So n minimum should be what? 2. I hope this clarifies your doubt.
Yes, thanks.
Yeah. Okay, it's past 5. I think I should end the session now. I hope you guys don't have any doubt pertaining to today's discussion. Abraham, are you fine? Any doubt? Yeah. Yeah. Okay. So to end the session, enjoy your weekend and have a nice day. We'll meet on the next weekend.
By
Next.
the way, do we have a session tomorrow, or we only have one session in Italian? Because session
I,
in tomorrow or Monday always announced but never happened.
I don't think so. I don't think so.
Okay, thanks.
Yeah.
Have a nice
Okay.
day and
Yeah.
weekend.
Bye. Yeah. Bye. Bye. Take care.
Thank you.
Yeah. Bye. Bye.